Today I will be presenting on microbially-induced carbonate precipitation versus enzyme-induced carbonate precipitation. In this presentation, I'll be referring to microbially-induced carbonate precipitation as MICP and enzyme-induced carbonate precipitation as EICP. Both MICP and EICP are emerging techniques within biogeotechnological engineering that have the potential to be heavily utilized for ground improvement and soil stabilization. Both MICP and EICP share nearly indistinguishable processes. In general, microbes or enzymes are utilized to create carbonate precipitation into the soil matrix that can help strengthen the soil. In 1980, Rachel Levy authored an article regarding the precipitation of carbonates in soils. She found that calcium, magnesium, and bicarbonate sources from the soil helped in the facilitation of the precipitation of carbonates. This research was useful in determining the conditions in which carbonates are precipitated most effectively. In 2010, Ginger Krieg Dozier first developed the MIC process and started a brick manufacturing company in which MICP is utilized to produce the material. The bricks shown in the images were produced by her company, Biomason. Ever since, MICP research seems to have diversified to test whether other issues are able to be solved with this process. As research is expanding upon MICP and EICP, possible applications for this technology is also growing. MICP is being tested as a remediation technique for materials like concrete and granite that have a high potential for cracking. MICP has the possibility to remediate radionuclide and heavy metal contamination. MICP has shown the ability to extend the service life of concrete. MICP has the potential to assist in the rubber and plastics industry, acting as a filler for the material. And MICP has tested as a solution to liquefiable sand, as the shear strength, compressive strength, and other properties can be improved with precipitated carbonates. MICP is achieved through urea hydrolysis, as it provides the most efficient calcite conversion rate. Urea hydrolysis is a chemical process in which urea combines with water to form ammonium and carbonate, and to produce calcium carbonate, calcium plus carbonate is required to form a calcium carbonate. In order to activate the chemical reaction, a urease enzyme is required to decompose the urea. In MICP, the urea enzyme is produced by the urease-producing microorganisms. Calcium carbonate is the desired final product of the reactants, as it is gelatinous. The calcium carbonate precipitate is able to bond to particles, giving it the potential to bring soil particles closer together and take up more space. While most researchers choose to trigger carbonate precipitation utilizing urea hydrolysis, other effective mechanisms do exist. Sulfate production, denitrification, and ion reduction are other methods that behave appropriately. EICP deviates from MICP in that the enzyme that induces the reaction is added to the environment separately rather than introducing the microorganism to the environment. The general idea behind EICP is that the chemical process should advance at a much quicker pace, as the enzyme does not need time to be produced. The urease enzyme is widely available and easy to obtain. The urease can be collected from beans and seeds from many plants from several different families. One of the critical steps of MICP is choosing an effective bacteria that can produce calcium carbonate efficiently in the selected environment. Some microorganisms are more resilient to extreme temperatures or unique pH conditions than other microorganisms. Furthermore, it appears that the more bacteria added, the better the efficiency of MICP is. Microorganism concentrations have a direct impact on urea hydrolysis. Urea hydrolysis is also heavily temperature dependent. Most urease enzymes are the most efficient between 20 and 37 degrees Celsius. However, this is dependent upon environmental conditions and the concentration of reactants within the system. When the temperature and conditions are not within the optimal range for the reaction, the urease activity decreases drastically. Also, pH has a major influence on carbonate precipitation. The urease enzyme is only active at certain pH values during urea hydrolysis. During calcite precipitation, the ideal pH range is between 8.7 and 9.5. A low pH value could yield carbonate that does not precipitate. MICP and EICP are nearly indistinguishable. It would be expected that they would yield similar results in terms of efficiency. The difference in how the enzyme is received by the environment may play a role in how well the enzyme can advance the reaction in the makeup of the resulting cemented crystal. An experiment was performed in which the strength of calcium carbonate produced utilizing urease derived from a plant and the strength of calcium carbonate making use of urease generated by a microbe were compared. The microbe that was used exhibited high urease activity. It was found that the strength of calcium carbonate in the sand cemented with the enzyme was superior to that of sand cemented with the microbe-generated urease. It was concluded that the enzyme was able to produce more effective crystals because it had a lower activation rate. Another experiment tested the effect of MICP and EICP on the permeability of soil. The permeability profile reduction of porous soils treated with bacterial-formed calcium carbonate and enzyme-formed calcium carbonate. The free urease enzyme was found to be more active than the enzyme generated from microorganisms. Additionally, as the number of enzymes and reactants that were added to the environment increased, the permeability of the soil decreased. It is clear that MICP and EICP present a significant opportunity to revolutionize the biogeotechnical engineering field. From the studies performed comparing the efficacy of EICP in comparison to the efficacy of MICP, EICP produces superior results in terms of strength and permeability. In a lab scenario, the results indicate that EICP is the preferred method as the rate and quality of calcium carbonate cemented crystals is superior to those produced by MICP. It is encouraging that MICP and EICP are being thoroughly tested as a solution to numerous issues, and I hope this innovative method can solve multiple challenges that the world is faced with in the future.